17.1b notes. Start with, even though the title is Finding a Trig Ratio from a given trig ratio, starts with a little bit about what's a rational number, how do we rationalize denominators. I never know exactly how much of this got covered in IM2, so we'll go through it quickly. Skip to page 2 if you think you already know this stuff. Rational numbers are any number that can be written as a fraction of integers. 1/2. That's a proper fraction, small on top, big on the bottom. Happens to be positive. Then my next example is negative 56 over 27. Happens to be negative. It's okay to have negatives. Happens to be improper, big number on top. It can still be a rational number. 5.2 looks like a decimal, and the definition says it has to be written as a fraction, or it can be written as a fraction. 5.2 is actually 5 and 2/10. And if I go way back, I can say 5 times 10 is 50 plus 2. I'll write that as 52/10. So yes, it can be written as a fraction. The next one is a decimal with a bar on it. That means it repeats forever. 0, 0.333, forever and ever. And a lot of us know that is the same as 1/3. Those repeating decimals, they can always be converted into a fraction. Even if you don't know what fraction they are, they're still good rational numbers. We won't mostly be dealing with decimals today, but I just want you to know. Square root of 100. Square root of 100 simplifies to 10. And yes, 10 can be written as a fraction, 10 over 1. Some examples of things that cannot be considered rational, irrational numbers. Pi. We've worked with pi enough in many years of math to know that it goes forever. It never ends. It never forms a repeating pattern. The same thing with the e that we worked with back in Mod 13. Root 2, 1.414, I don't even know what the rest of it is. It goes forever and never forms a repeating pattern. Another example is when you have a nice whole number multiplied by a radical that doesn't work out. Those are all examples of irrational numbers. In part of today's assignment, they asked for exact answers, not decimal approximations. We're still going to have some of those solve the triangles where they ask for decimals, so read the directions carefully. In fractions form, we sometimes have radicals within the fraction that cannot simplify down to integers, so the final answer will be irrational. But we're going to rationalize the denominator, which means radicals are allowed, they're just not allowed on the bottom of the fraction. Really rough example with letters. If I have w root z over x root y, I don't have a problem with the radical on the top. I have a problem with the radical on the bottom. So I'm going to take this and multiply the radical I'm trying to get rid of, which means the top of this is now w outside square root. The z and the y come together inside the same radical. At the bottom I have my x, and I have the square root of y squared. The square root of y squared is just y. Again, make sure that fraction bar comes all the way to the end. That's a little strange. Let me do some examples with numbers in them. If I start with 2 over the square root of 7, I don't want to have a radical on the bottom. So I multiply by radical 7 and radical 7. The reason we can get away with multiplying the top and the bottom by radical 7 without changing the value is because root 7 over root 7 is just 1. Multiplying by 1 changes the way something looks. It doesn't necessarily change the way its value turns out to be. So the top of this is now 2 square root 7. The bottom is the square root of 7 times 7, the square root of 49. And just like the example above, when we did the square root of 7 squared, we ended up with just 7. Square root of 49 is just 7, and I have 2 root 7. Shorter way to look at it is root 7 times root 7 is just going to be 7. Why go through the root 49 in the middle? We'll come back to this fraction. Some people are tempted to say, I got 7 on the top, 7 on the bottom, but we can't reduce them. a 7 inside the radical, a 7 outside the radical, cannot be reduced. That's as far as that one can go. If, however, I look at this second problem, I've got a 3 and a 15, which look like they could reduce each other. And since they're both inside the radical, I can. 3 goes into there once, 3 goes into there 5. This is just going to turn into square root of 1 over square root of 5. And I know that the square root of 1 is just 1. But I'm not allowed to leave that radical on the bottom. So let's say, got to get rid of the radical on the bottom. I'm going to multiply root 5, top and bottom. And yes, I do want to show that stuff. Eventually, mod 18, we could start skipping that stuff maybe. But right now, I want to see it. This turns into 1 times root 5, which is just root 5. Root 5 times root 5, which is root 25. But I don't bother to write that just step down because root 25 is just 5. It doesn't make the bottom disappear. It just turns the bottom into a whole number. And again, I've got a situation with root 5 over plane 5, both 5s, but one's inside the radical, one's not inside the radical. I can't do much with that. Let's look at the third one. I've got radicals on the bottom, and some people would want to multiply the top and the bottom by 2 root 5, and it will work out, but it's work that you don't need to do. The one thing I'm trying to get rid of is the root 5, so I'm multiplying top and bottom both by root 5. And you know, I think that while I'm at it, let's save some time later and say 2 and negative 12 can reduce each other. I don't want to have to reduce it later. So this turns into negative 6. And I've got that root 5 on it. And I have root 5 times root 5, which is root 25. Nobody needs to write that down. Turns into plane 5. And 1 times 5 just leaves a plane 5 on the bottom. And that's a final answer for that one. Now look back to this middle one for a minute and show you a different way I could have done this problem. If I started with root 3 over root 15, and I didn't happen to notice that 3 and 15 reduced, or I didn't know it would work that way, I could multiply by root 15. The bottom would be root 15 times root 15 is square root of 225, plain old 15. The top is the square root of 45. But in this case, we have 45, which can split up to 5 times 9, 3 times 3, pair of 3's, left over 5. So I'm going to turn the top of this fraction into 3 square root 5 over 15. And then 3 goes in once, 3 goes in 5, root 5 over plane 5. Same answer that I got over here, just a little longer in case you just didn't happen to think about reducing before you started. Same thing could happen with this third example here. If I had not reduced the 6 from the 2 and 12 in the first place, I still could have reduced it later. It still would have worked out. Okay, let's look at more examples of multiplying radicals together. This one says we can multiply expressions with radicals with roots in them by multiplying the outside two numbers together, putting that on the outside, multiplying the inside two numbers, putting it on the inside. We would always say simplify if possible. I'll show you an example where it's possible to simplify, and then one where it's not, where it is, and one where it isn't. Let's do first the one where it's not possible to simplify. So what if I start with 5 square root 2 times 7 7 square root 3. I'm going to do 5 times 7, put a 35 on the outside. I'm going to do 2 times 3, put that on the inside. And since square root 6 has no exact square root, and it doesn't break up to give you any pairs, that's all we can do with that one. Here's another example where we can do a little bit more. What if I started out with 3 root 2 times 5 root 8? Certainly I could simplify root 8 first, but I'm going to wait and deal with it after it's done. I'm going to say 3 times 5, 15. I'm going to say 2 times 8, 16. Can't do anything with the 15, but I do know the square root of 16 is 4. And this is going to turn into 60. So sometimes you can start with an irrational expression times another irrational expression and still turn out to be a nice whole number, a nice rational number. That happens every time we square a radical. We will always get a whole number answer. You can put it in your calculator. If you put it in the parentheses all in the right place, you'll still get the right answer, but there's so much troubles with accidentally messing up your parentheses that I don't like to do that. It does say this part gets squared, this part gets squared, but we saw above the square root of y squared will always turn out to just be y. So here's a number example. 5 square root of 7 squared becomes square the 5 part and square the root 7 part. But 5 squared is 25. Root 7 squared is root 49, which just means 7. I usually skip this step and say 5 squared is 25, root 7 squared is 7. And then I just multiply to say 25 times 7, 175. It's really quicker than trying to figure out all the parentheses in your calculator. We're going to have to use both of those things in the next section. Okay, here's all that again, typed in case my writing was a little sloppy. And then we're going to go on to the bottom half of these notes. This section, they're giving us one of the trig ratios. They might give us sine, cosine, tangent, and then ask us to find one more. Or sometimes, since there are 3 trig ratios possible, sine, cosine, and tangent, they might ask you to find both of the other ones. In order to do that, what you need to deal with is analyzing opposite, adjacent, hypotenuse. Now, nobody told you the exact sizes, but you can use a similar triangle with these numbers. So let me start with what I know in this case is cosine of theta. This is Greek letter theta. And I may have talked about this before, but theta is a line with a circle with a line straight across. It is not that. Do not write that. That means the null set. It's not what I'm talking about. Some people try and do it this way. Looks like a cursive O. I don't like that either. What I want to see is straight across. If you are one of those people who just loves that cursive O, make sure you bring your line down halfway so that it doesn't look like an O, it looks like a theta. Okay. What we know is cosine theta equals 2 root 6 over 7. What we want to know is tangent theta. Let's think about what we know. Cosine is adjacent over hypotenuse. So this side has to be adjacent, and this side has to be my hypotenuse. Let me come down here and write it down. My adjacent side, 2 root 6. My hypotenuse is 7. I need to find my tangent. In order to find my tangent, I'm going to have to know the opposite side and the adjacent side. It looks like I already know the adjacent side, 2 root 6. But I don't know the opposite. Let me put these on a triangle for those of you who need the triangle, but I think most of you will stop using the triangle after a while. Here we have theta, and there's the side opposite theta. I don't know that one yet. And then we have a hypotenuse, opposite from the right angle by our hypotenuse. I know that that is 7. And the one that touches theta is my adjacent side, and I know that that is 2 root 6. So I'm looking at a right triangle, and I need to know the opposite side. That's what I'm aiming for. So I'm going to come over here, and I'm going to look at what I know and use it to find out what I don't know. I'm using Pythagorean theorem. Pythagorean theorem is a squared plus b squared equals c squared. But in this case, I'm going to call that the opposite squared plus the adjacent squared equals the hypotenuse squared. And certainly in my note, in my homework, I wouldn't bother to write all those words out, but I want you to know what's going on. I don't know the opposite. I'm going to call it a. I do know the adjacent, 2 root 6, which I'm going to square. And I do know the hypotenuse, which is 7, which I'm going to square. Take a minute, look at 2 root 6. We just did the first part of the notes where we talked about how do we square these. So I'm just going to say 2 squared is 4, and root 6 squared is 6. So that now I have a squared plus 24 equals 49. And I want the a by itself, so let's do minus 24 on both sides. And that gives me a squared equals 25. Oh, this one's nice. I'm going to be able to use a nice whole number this time. Square root on both sides. Yes, please show me the square root symbol. A equals 5. Good. And we said a was my opposite. So I'm going to come over here and write opposite side was 5. And what I want to know for my tangent is the opposite over the adjacent. I already filled in my adjacent. I need to fill in my opposite. Now, we can't leave that radical on the bottom. So we're going to rewrite this as tangent theta equals 5 over 2 root 6. And yes, I like for that fraction bar to come all the way to the end. And I did get rid of the radical on the bottom. So since there's a root 6 on the bottom, I'm going to multiply this by root 6, root 6. Okay, top of this fraction, 5 square root 6. Bottom of this fraction, I still have the 2. I have root 6 times root 6, which is root 36. But we're just writing down simple 6 for that. 5 root 6 over 12. 5 and 12 don't reduce. You might be tempted to reduce the 6 and 12, but one's inside the radical, one's not inside the radical. I can't reduce it. So I'm going to end up with a final answer that says the tangent of theta equals 5 root 6 over. The next example wants us to find sine given tangent. So let's write down what we know. The tangent of theta equals 3 root 3 over 5. Let's write down what we want to know, the sine of theta. Okay, tangent from up here is opposite over hypotenuse. Opposite hypotenuse. come over here and I'm going to write the opposite is 3 root 3. The hypotenuse is 5. I need to still work on finding the adjacent. If it makes you feel better to do it on a triangle, we can do it on a triangle as well. Opposite from the theta, that means not touching the theta here, is 3 root 3. Don't know this adjacent one yet. We're going to figure it out. And we know the hypotenuse over here is 5. This was our opposite. This was our hypotenuse. This is our unknown adjacent side. I usually don't bother to draw the triangle after I've done a few of these. I need to know the sign. And sine is always opposite over hypotenuse. So opposite over hypotenuse. If I look at the one that I know the opposite. So I can write sine theta equals 3 root 3. I certainly wish I knew how to edit a video without going back and re-recording the last 20 minutes. So stop a minute, notice that I paused, I erased some things that I found out were wrong. I wrote tangent was opposite over hypotenuse when tangent is opposite over adjacent. If I come over here, that means the adjacent side is 5. The one that's touching the theta is 5. The one that I don't know is my hypotenuse. I severely apologize. Maybe someday I'll figure out how to edit a recording. Maybe someday I'll figure out that it's not going to take me forever to re-record. But we got to live with this for the moment. Okay, opposite over adjacent. I need to say, I already know my opposite side was 3 root 3. I don't know my hypotenuse. That's the one I'm going to have to work on right now. I'm going to come over to the ones that I know and say Pythagorean theorem. Opposite squared plus the adjacent squared equals the hypotenuse squared. In this case, I know the opposite is 3 root 3. I'm going to square that. I know the adjacent is 5. I'm going to square that. And I don't know the hypotenuse, so I'll use a C. Now, 25 out of 5 squared is pretty easy. 3 root 3 is going to be 3 root 3 squared is 3 squared is 9. Root 3 squared is 3. So that's just 27. I'm looking at 27 plus 25. 52 equals C squared. Take the square root on both sides. Again, no need to worry about plus minus when you're dealing with the sides of a triangle. I need to split up my 52. I'm going to come over to the left, split up my 52. What goes into 52? I know cards well enough to know that there are 52 cards in a deck, and a deck of cards has 4 suits, each with 13 cards. 4 times 4 splits to 2, so I get a pair of 2s and a leftover 13. So I have 2 square root 13. This section does say we need exact answers, so I can't change it into a decimal approximation. Now that I know my hypotenuse, I can bring it on over here and write down 2 square root 13. I have radicals on top, I have radicals on the bottom. Unfortunately, they don't reduce each other. The outside numbers, they don't reduce each other. I'm going to say I need to get rid of the radical that is on the bottom. And the one that's on the bottom is the square root of 13. I don't need to multiply by the top one. I'm not trying to get rid of that. Multiply by square root 13, square root of 13. Again, I'm multiplying by 1. It's going to change the way it looks, but it's not going to change its value. So that I end up with a 3 and a square root 39. On the bottom I get a 2, and root 13 times root 13 happens to be root 169. That doesn't really matter because we know that square root 13 times square root 13 has to turn into just 13. I take a look and I say 3 doesn't reduce with 2, 3 doesn't reduce with 13. The bottom's going to turn into 26. I have that 3. I'll try and split up my 39, but I get 2 and 13, no pairs. So this is just going to have to stay square root 39. And that is my answer for sine theta. Final answer. Okay. There are several problems like this in tonight's assignment. I will take time to make a video that covers some of those. Again, I apologize for my mistake. Maybe I'll re-record later, but for now, at least you have something. Make sure you watch my videos if you're still confused.